Okay, so this is our last lecture together, and my plan is twofold, is to finish the topic that I started yesterday and that you also developed during the exercises given by Francesca, which is related to gamma rays. And then we will come back a little bit on the transport equation, find the way to solve it and see some results from experiments and from groups that try to interpret the most recent data, if we have time to do everything. So, going back to gamma rays, I would like to discuss the gamma ray sky as we know today. Today it means 2018, 2019. So the gamma ray sky is being measured in the best way that we have so far by an experiment which has been sent to space by a rocket in 2008. The experiment is the Fermi Large Area Telescope, and within this detector, gamma rays are measured between a very small energy, which is, let's say, 20 MeV, and up to more than 300 GeV. In this energy range, the photons arrive at the detector with, of course, I mean, what I wanted to say is the contrary. The detector has an angular aperture and angular resolution which changes with energy. So the photons that arrive on the Large Area Telescope are not all once detected with the same angular precision. So for purposes linked to dark matter searches and the understanding of sources in the sky, usually one considers energy above 100 MeV. Nevertheless, I don't want to tell you any technical details of this experiment. It is not this the place. Just know that it takes data in an all-sky mode. So every 1 hour and a half it completes an orbit, and it has a 70 degrees half angle of view. So any point of the sky is seen by Fermi for half an hour every 2 orbits, so every 3 hours. So it is really a great opportunity that astroparticle physicists have since the Fermilab starting time. So this is a picture that we have produced, I think 1 year ago within our group. Being the Fermilab and NASA experiment, the data are public, so anybody of you who wants to analyze Fermilab data in principle can be. The collaboration puts a lot of software for elaborating the data, so also myself and my collaborators who are not, or at least not all in the Fermi collaboration, can do this kind of analysis. So this is the all-sky view seen by Fermi between 1 and 2 GeV. This is the number of photons in each pixel. So here the counts are much, much higher, and this is the galactic disk with all the gas and all the sources. And this is the same sky, but in another energy beam between 2 and 5 GeV. And this is the sky, well, maybe it's not so clear, but it is much, much darker, between 5 and 10 GeV. So increasing the energy, Fermilab receives less photons. And this is due to the physics of the sources. Normally, the sources of gamma rays, as cosmic rays as well, have energy-dependent source spectra that go as a power law. So this is the physics that explains why, the physics, some hint, of course, that explains why this figure is getting darker and darker with increasing energy. So the photons now are at most 3,000, 3,500 per pixel, and at higher energies, you see they were a significant factor higher. So let me discuss how these photons are produced in the sky. So these are all sky photons coming from any source, any possible dark matter annihilation, and whatever. So let's see together the gamma ray emission. And this is, you will see in a while, strongly linked to what we have seen in the previous lectures. So the gamma ray emission is predicted for the interactions of cosmic rays with galactic gas. And this galactic gas is atomic hydrogen, ionized hydrogen, and some gas which escapes most of the observation, which is called dark neutral gas. And the interaction is that a cosmic ray, and mostly proton and helium in the cosmic radiation, plus one molecule of gas, or one proton, undergoes a totally inelastic interaction, and hadronic processes occur that then give rise to pi zero plus anything, and this pi zero immediately decay into photons. And then we have in the sky the inverse Compton emission we have seen a few days ago. So if electrons lose energy by inverse Compton, on the other side we have photons in the gamma ray sky that have been upscattered in energy by these electrons. And so for cosmic rays, so electrons in cosmic rays that interact with the interstellar radiation field. So I remind you that an electron plus a photon with some energy is interacting, and the electron upscatters the photon. So the energy of the final state photon is greater than the starting energy. Good. Then we have an emission which is measured to be isotropic, and it is particularly visible when studying the gamma ray sky at high latitudes. And this isotropic emission is very likely of extragalactic emission origin, and it is, again, a background, or it depends what we want to study, but it is present everywhere, because since it is very likely of extragalactic origin, every point you move your telescope, it is there. All these emissions that I wrote at the blackboard are diffuse emissions, so there is not a specific point source. But we know that the telescope has measured a very large number of point sources. And a few days ago, the Fermilab Collaboration has published the 4th source catalog. You can find the paper on arXiv. And in this release, they have analyzed 8 years of data. It is not that trivial to analyze data, so they have this result on the first 8 over 10 years of data, and they have measured 5,098 sources, which is, of course, the biggest gamma-ray catalog that we have so far. Among these sources, there are 75 sources which are even extended. So they are not measured as point sources, but the telescope can detect and can resolve an extension. The biggest extended sources are indeed, let's say, structures. One of these is the so-called Fermi bubble that has been detected a few years ago, and these are enormous structures across the galactic plane. There is another big structure which is called Loop 1, and then there are sources, astrophysical sources, that have been detected as spatially extended. Many of these sources are linked to active galactic nuclei. In particular, they are blazars. And of course, these are all extragalactic sources. A number of sources which is pretty high, it is 241, has been measured to be pulsars, which is one of the big results of the Fermi Large Area Telescope, to have measured an incredibly high number of pulsars with respect to the state of the art. And there is another point that I want to underline in this catalog. There is a number of sources, which is about 1,500, which in the vocabulary of astrophysicists is unassociated. These are particularly interesting sources. Unassociated means that they have no counterpart at any wavelength. Usually one points a source and finds an axis and is sure that there is a source there, and immediately people look at catalogs, mostly at radio catalogs, to see if in the same place of the sky somebody has seen a source, and this emission, for example, in the radio wave, is compatible with what people is measuring in gamma rays. Well, there is a significant fraction of sources that at the moment is not associated to any radio, X-ray, visible, or whatever wavelength. And now it's happening that people measuring gamma ray unassociated gamma ray sources are asking to colleagues working, for example, at radio telescopes, to look in that precise portion of the sky to see if, looking with more detail and knowing the position, this source is possible to see. This is really a big and very interesting multi-wavelength interaction that has been improving since these catalogs among different astrophysical communities. Then I don't want to So let me come back. So we have point sources. We have extended sources that, if you want to predict the gamma ray sky, must be put in a very different way when you try to predict the Fermilab sky. And then there are some residual photons from the Earth and the moon limb, but they are not very relevant above, let's say, 200 MeV. So they, in many analyses, they are modeled and or they can even be neglected. So you see, we have the point 1 emission, which is fully galactic. The second one is, again, fully galactic. The isotropic is very likely extragalactic, and point sources, it depends. Pulsars are mostly galactic, KGN are extragalactic. The first two emissions are composing the so-called galactic diffuse emission, which is a kind of sea of photons produced by all the scatters of cosmic rays on the gas and on the interstellar radiation field. This galactic diffuse emission is dominant, and it is dominant almost at all latitudes. Of course, going towards the galactic plane, it is overwhelming. Going to higher latitudes, it is a bit less relevant, but it is almost everywhere, at least 50% of the photons that you measure in the sky. So, if you are interested in studying the galactic diffuse emission, well, it is almost everywhere, so one has a lot of places to try to understand it. But if you want to measure anything else, for example, some possible dark matter annihilation or studying extended sources or anything else, it is, well, not really a background, it is a foreground, because between you and any other source there is always this thickness of photons that you cannot avoid. There is no way to subtract this foreground. So the only way that physicists have to deal with it is to model in the best way and then to put it as a template and do all the other analysis with some assumption about the galactic diffuse emission. So the galactic diffuse emission is cosmic rays, and these cosmic rays are proton, helium, and nuclei. The target can be the gas, and the gamma rays, in this case, are given by pi 0 decay into 2 gamma, or the sources are E plus E minus that interact on the interstellar radiation field and give photons via inverse Compton. There is also, well, just for completeness, I put it. I didn't spend time on that, but I mean, you can easily recover the physics of this. There are also electrons that can interact on the gas and give photons via Bremsstrahlung. So, in order to predict the galactic diffuse emission, or to determine the galactic diffuse emission, one should, in principle, perfectly know the cosmic rays, and the cosmic rays in every point of the galaxy. We only have detectors at the Earth, so we should know how protons are behaving in, for example, in some spiral arm of the galaxy. They are not necessarily the same flux as we measure here. We must know the distribution of gas, and we must know the interstellar radiation field. So it is a big work to arrive at a determination of the diffuse emission, the gamma-ray diffuse emission. The gas comes under the three forms, H1, H2, and also the molecular hydrogen. So this is neutral atomic. This is ionized, which is a fancy way to say that it is protons. And there is molecular hydrogen. This gas must be measured in all the places of the galactic plane, or where it is anyway, also out of the galactic plane. And there are very intense and very difficult surveys that try to measure we call the column density of the gas along a line of sight. Moreover, the gas comes at different temperatures. So according if it is cold, if it is warm, or if it is hot, the physics is different, and also the measurements can be a bit different. There are some more notes that you can find here if you are interested. Just what I want to say is that one of the most interesting tools to measure the gas, the distribution of gas, is an emission line, which is very important in astronomy and which is called the 21 centimeter line. And this 21 centimeter line is connected to this quantum mechanics transition in the hyperfine structure of H atom. So it happens when the atomic hydrogen, it is in the fundamental state, but the spins of electrons and protons can be whether aligned, whether opposite. So there is a splitting of the energetic states of the atom, and the splitting between two states is of about 5.9, 10 to the minus 6 electron volt. This is really hyperfine with respect to the energy levels of hydrogen. And this is when the spin are aligned, and this is when the spin are opposite. So the upper level, when the spins are aligned, can go to the lower level when the spin of protons and electrons are opposite, emitting a photon. So the stabilization of the quantum level comes with the emission of a photon. And this photon, with this energy, has the frequencies, the corresponding frequency of 1.42 gigahertz, which is radio close to microwave. And the wavelength is 21 centimeter. This is why these 21 centimeter surveys are named. So with radio telescopes that can make deep survey, one can reconstruct the column density of gas in, let's say, in the galaxy. And you can imagine yourself that it is not a trivial task to have a map of gas for all the galaxy. And for all the three states of hydrogen and for all the temperature it comes with. Some other lines are measured. For example, measuring the molecular hydrogen is not possible via this way. But people measure another transition, which is the transition of carbon oxide, how to say? And there is an emission line of this molecule, and this molecule is very often associated to the presence of H2. So the emission of CO is a tracer for the distribution of molecular hydrogen. This line for the emission of CO is at a wavelength of 2.6 millimeter. That means a frequency of about 100 gigahertz. So, in the lucky hypothesis in which our colleagues working at different wavelengths and studying also the interstellar radiation field provide us with map for any component, we can hope to have a prediction for the galactic diffuse emission. So, since, as I was telling you, the galactic diffuse emission is unavoidable and it is a foreground for any measurements, what people, in particular the Fermilab Collaboration, has done is the following. Well, it is impossible to predict the diffuse emission in all points of the galaxy because we don't know cosmic rays everywhere, or at least it is difficult. What they did is to have maps for the gas, for the interstellar radiation field, and try to make hypotheses also for all the other components, and to make a prediction for the entire sky. So the idea is to predict the whole gamma-ray sky. This is, of course, a prediction, which is a function of latitude, of longitude, latitude, and energy. And it needs the distribution of H1. And the distribution of H1 is a function of coordinates. And there is a factor in front of this distribution, which is a function of energy, and it says how photons and at which intensity and at which energy are produced in any point where we have this gas. And then there is the same structure. This coefficient Q is called emissivity for any of these components. So there is CO, the column density is called W for CO, and it traces mostly molecular hydrogen. And then there is a similar emissivity for the dark neutral medium, whose determination is even more difficult than the previous two ones. You can read, there are some papers on that if you're interested. And this is the dark neutral medium, which is again convolved with the spatial distribution. Then there is a term that I don't want to, I just put for completeness, which corrects somehow the distribution of H1. Just take it for granted, because otherwise times runs. You can take the Fermi paper if you want to better understand this little correction. And then let's come to our so to the components that we have studied better in this course. which is the inverse Compton. And this is the inverse Compton normalization factor. It is a function of the energy, and it is convolved with the maps for the interstellar radiation field. And this comes with an energy because it is ultraviolet, it is visible, it is infrared, and it is the CMB. So you have a distribution on all the wavelengths, which is different. Then one should predict, we should make an hypothesis for the extended sources, which has a position in the sky which is not point-like. So, and then there is the isotropic distribution I told you before, which is a function of energy and which is preferably determined at high latitudes, but when people do this full sky prediction, put a kind of free normalization to let it vary to better fit the whole gamma ray sky. And then there are the point-like sources. The point-like sources are a sum on all the point-like sources, so kind of 5,000 sources that you have to include if you want to predict the correct gamma ray sky. And these have a flux, and they are located in a precise position of the galaxy. So this is J, and this is B minus Bj. And then I don't add, well, we can put everything together, but the last point is much less relevant. There are some photons that hit the detector and that are given by the Earth limb. And some contribution that one should model that come from the sun and from the moon. Okay, so this is the full way to write the gamma ray sky. And what people usually do is that, well, this component here, in particular sun and moon, are fixed. So they are determined independently. But all the other components have the emissivities or the normalizations let free. So emissivities are one. This is the normalization for the inverse Compton, for the extended sources, and this again, point sources, let's make the hypothesis that this one detect them are more or less known, but one can leave the normalization of the flux of point sources also to vary. And, but usually they are taken from the catalog. And eventually also this component. So the big exercise that the Fermilab people are doing and have done in the past, and also some other collaborators, is to fit all the sky and to give results for all the quantities that I have underlined. The statistics of photons is significant, so it is an exercise that brings to stable results. I mean, to not stable, yeah, but to precise results. And this is one of the results that I wanted to show, because it is, I think understandable with the tools that we have developed together this week. These are the results for the different components that fill the gamma-ray sky, and the result is out of the galactic plane. This is the latitude, so 10 degrees out of the galactic plane, so from 10 to 90, and this is around the galactic plane by 10 degrees slice. So, I don't know if it is, you can probably read, the red is pi zero, almost pi zero plus Bremsstrahlung, but photons from mostly pi zero decay. And you see that at high latitudes, it is dominating the sky. And then there is the second component, which is this light blue, which is inverse Compton emission. So let's concentrate on these two components. Look at the galactic plane, around the galactic plane. There is as well some important inverse Compton emission. There is also pi zero and Bremsstrahlung. So the red, now I specify, the red is for hydrogen, H1, and the green is for molecular hydrogen. So they have split it even on these two different targets. But you can see that around the galactic plane, the pi zero plus Bremsstrahlung on H, atomic and molecular hydrogen, strongly dominates the sky. Going at higher latitudes, the gas decreases because it is mostly linked to the stellar activity and to the distribution of the gas in the disk, and the inverse Compton gets more relevant. The inverse Compton cannot be neglected even in the galactic plane, but it is not the main contributor. Also, extended emissions are not negligible. This is 2 years ago paper, so with new discoveries, maybe it could also be a little bit higher, I don't know. Anyway, if you want to make a precise analysis for your researches, also extended emission are more than %. So any physics which is few percent, in principle, can affect your result and must be included. Okay, this is what I wanted to say. You see also the energy dependence. The energy dependence of this components is pretty, well, not the same, but the place in which you have the most of the photons is in the GV region. And this was visible also from the maps that I showed you before. So from one side, it is a privileged place because you have a lot of photons. But you must be careful to very well model your galactic diffuse emission because it is an unavoidable foreground. Good. So this is more or less what I wanted to say about the gamma-ray sky. And now, given the relevance of this cosmic rays, I come back to what I started to discuss. I discussed even with some details in the previous lectures. And I would like to make you some more, to give you some more information about the charged particles, and not, this case, about photons. So before going to again to our transport equation, the transport equation, now you understand what it can mean to solve the transport equation in every point of the galaxy. It is It would be relevant, but it is really a difficult task. So let's come back to the sources of these cosmic rays. And I would like to spend a few words about sources which are typical of secondary nuclei. For primary sources, we have seen supernovae, we have seen pulsars. You have done some more learning on Tuesday afternoon. You have seen dark matter. These are the possible primary sources that we know. And then there are sources giving secondary nuclei. And secondary nuclei are really a valuable means of information in the galaxy. So now let's come back to charged cosmic rays and to secondary sources which are due to spallation reactions. So let me write in some more details how the distribution function for a secondary nucleus is given when a nucleus I produces this very nucleus J. This can happen at different energies and at any place in the galaxy. I avoid here a time dependence. Usually these sources are steady state. It is, we can put it, but it is for special cases. In order to compute this term, one must sum on all the nuclei I, which are the cosmic rays, that can make a spallation reaction. Then we have to sum on all the species of the interstellar medium. And we have to compute a convolution from a minimum energy, which is usually a kinematic threshold, let's say in principle to infinite, of the Ni nucleus times the cross section of the nucleus I over the nucleus K, where the then we have the velocity. I put P, but it is I. And then we have the density of the interstellar medium, which is given by different species. I see now that in my notes I forgot density, sorry, of the interstellar medium. So, in order to compute this class of nuclei, you have to know the cosmic rays, flux, the distribution of the gas, and a full set of cross sections. I was already hinting at this problem, and now I have some, where is it? Some figure. So you are not, of course, required to read this figure. It is just for your emotional reactions, how to say. This has been taken by a recent paper, and on the left side of this figure, these authors have listed all the possible reactions that occur in the galaxy and that produce lithium. So you say, okay, nice. Now AMS has measured the lithium flux. I want to predict it. Well, it's nice, but it is a huge work. These authors have also somehow ranked the relevance of each contribution, so at some point you can decide to stop adding contributions. But this is just to tell you, to show you that this physics require not only to know the flux of oxygen 16, of silicon 28, but you must know the cross sections. And the only way is to measure them at colliders. So this is a physics really that needs multi-wavelength and multi-messenger and multi-disciplines inputs in order to perform it, and to perform it with precision. Because now data from example, from AMS, and first also from Pamela, and there are other experiments, is pretty precise, and the data are provided with few % of errors, which is very similar to the precision of high-energy physics. So we cannot say, okay, I make some approximate. It is no longer possible, otherwise you miss the interpretation of some data point. And this is the same as before, but this time from beryllium. So you see that there are really a huge number of reactions that should be included to be at a very, very precise level of prediction. Maybe I have added 2 figures that I show. This is a typical work that people doing cross-section analysis are forced also. These are taken from the same paper as the huge tables. The aim, my aim for showing you this figure is that, well, there are some analytical models. This is, for example, the production of lithium-6 by carbon-12. And you see that we have some data, but even it's not really a clear situation from an experimental point of view. But for example, here, the production of nitrogen-14 by Mg24 has 1 data point. And then, well, you try to fit, you try to have some extrapolation for previous empirical models, but it's far from an easy task, and the uncertainties that this kind of physics brings to the prediction of secondary nuclei is often huge. And in the last years, it has become one of the most important sources of uncertainty. Maybe it was before, yes. Now let me show you this figure. This figure is kind of a summary of the different possible sources that we have in the galaxy. This is the atomic number, and this is the number of neutrons. That means that here you have a species, for example, beryllium, with different isotopes. Okay, so a species can come with different isotopes. So take a nucleus that you like, I don't know. We can, for example, consider oxygen, which is 8, Z equal to 8. It is mostly primary. Full red means that at least 75% is from sources, so from supernova remnants. But there is, where I am here, some secondary left, which is anyway less than 5%, which is not very relevant. And there is another another part which is mixed between primary and secondary, which is not so, let's say, easy to separate. For example, take lithium. Lithium is here. Lithium has two isotopes, and these two isotopes are fully secondaries. And so come back to the cross-section problems for this kind of nuclei. There is carbon. Carbon is mostly primary. It has a small secondary component given from the spallation of higher nuclei. And there is, you probably know by other ways, the 14 carbon, which is a radioactive isotope. It is often used as a clock, also to date back ancient objects. And it can also be produced in the galaxy. And this triangle here is propagation clock nuclei. Then there is the iron and very heavy nuclei. They are mostly primary, and iron and nickel mostly can break on the interstellar medium and give birth to this number of isotopes, which are called the sub-iron nuclei, that are fully secondary. So this is a kind of screenshot for the parenthood of nuclei and isotopes in the Milky Way. Indeed, the fact that there are secondary nuclei in the galaxy can be also deduced in this way. This blue line connects the abundances of the nuclei that you read here, so helium and hydrogen, lithium, beryllium, boron, CNO, and so on and so forth. The blue line is for the solar system, from the solar environment. And in our neighborhood, we don't have secondary nuclei. So the fact that, indeed, at the galactic level, we measure secondary nuclei, in particular lithium, beryllium, and boron. You can see here lithium, beryllium, and boron. They are almost fully secondary. The fact that they are not present in the solar system for lithium, LiBeB, and also for the sub-iron really means that there is a mechanism in the galaxy that permits the creation of these secondaries, and so far we understand it as spallations of heavier nuclei. Okay, so now I briefly go back to the transport equation that we have seen a few times and try to give you just some very indicative tools in order to solve it. So I don't write the transport equation once more. You always have it in mind or in your notes. It is an equation which is in principle is three-dimensional in space, and there is a coupled equation in energy, which is, I derived you a second-order differential equation also in energy to keep into account reacceleration, and at first order also energy losses. So how can we solve it? Well, in principle, you can do a numerical solution. So solving numerically both the space and the energy part term. Anyway, whatever is your solution scheme, you must make an hypothesis on the geometry of your galaxy, because you have to decide where to put the acceleration, where to put the sources, where to put the interstellar medium. So a way of seeing our galaxy from a cosmic ray point of view is to imagine it as a cylinder. And, well, of course, my picture is a bit... you force me to use the blackboard, and then I have very bad pictures. I'm sorry. But it is very easy to put keywords on Google and to find better explanations. But we derive together, so it is maybe easier to understand and to memorize it. So this is the galactic disk, where we have sources and gas, all the sources and all the gas that I described you before. This is the galactic center. This is our position. The radius of our galactic disk is about 20 kiloparsecs. And the thickness, which I call h, usually h is the half thickness, is 100 parsecs. So the full thickness is 2h. This is an approximation, but just to give you the numbers that are typical for this situation. And the distance of the Sun to the galactic center is about 8.5. So this is the distance to the galactic center, and it is more or less 8.5 kiloparsecs, according to the years, of course. And then there is very likely, we are almost sure about that, we cannot avoid to include this zone above and below the galactic disk, in which the gas is very rare, but that is not true for the magnetic disk, for the magnetic fields. This is mostly evident for external galaxies. I was hinting this a few lectures ago. The fact that we measure radio emission at high eighths from the galactic planes of some external galaxies. That means that if there is emission at radio wavelength, there is some very likely synchrotron process taking on, and then magnetic fields. If there are magnetic fields, our particles run in these magnetic fields. So the diffusion coefficient and the transport of cosmic rays happens everywhere, also in this diffusive zone, which is called the halo of the galaxy. Then there are many halos, because there is this diffusive halo and there is also the dark halo, so don't confuse. And when solving the diffusion equation, one has to evaluate well where all the processes occur. We have the disk, and we have the diffusive halo. This is one way of modeling the galaxies. It is not the only one, but of course it is the simplest and to the aim of our lectures, also the one that gives you the most easy understanding. This is used by several groups, indeed, when solving the transport equation. So it's not only a toy model, it is a realistic model. So this is the diffusive halo, and this is the disk. The eighth of the halo is not very well determined. Anyway, it is of the order of at least a few kiloparsecs. Let's say 2, maybe 5, even 10 kiloparsecs is still, I think it is still possible, is it? Yeah. Indeed, we are, I mean, recent analysis favor high halos than very small halos, so it is probably to exclude 1 kiloparsecs halo, but 10 is possible. So if you have in mind the diffusion equation, we have sources, primary sources. In this scheme, they are in the disk and they are not in the halo. And then we have magnetic field, magnetic fields, that mean diffusion, and diffusion is everywhere. And then we have convection. I was maybe not very detailed on this. Anyway, you remember there is a gradient of the convection velocity. Anyway, very likely, no, not very likely, convection is everywhere in the galaxy. Then we have reacceleration, and this, well, surely it happens in the disk, and it can also be set in the halo. There are different ways of modeling reacceleration, but mostly, of course, it is in the disk where the magnetic turbulence is very high. Then there are Coulomb and ionization energy losses. These happen in the disk, not in the halo because there are no targets. Then there is synchrotron emission, let's say synchrotron energy losses. Since magnetic fields are everywhere, this must be set everywhere. And then there are inverse Compton losses. And the inverse Compton losses are, in principle, everywhere, because electrons propagate also in the diffusive halo, and at least the CMB is in the halo. These are, I'm discussing here the losses. And then, if you want to include the dark matter, well, dark matter is present in an even bigger halo than the diffusive halo, so that's sure that dark matter, if it is there, is everywhere. So, when solving your transport equation, even if you have made the simplifying hypothesis that the galaxies is a sandwich, is kind of a disk with two diffusive half halos, it is not that easy, the solution, because, for example, you see that energy losses, some are only in the disk, some are everywhere, and the solution is not that easy. In fact, there are few groups in the world that have full codes for the solution of cosmic rays. It's not something that you write for all the nuclei, of course. If you want to concentrate for one species, it is a bit more easy. Anyway, given this cylindrical symmetry, there is one mathematical help. So if cylindric symmetry is there, and in some other assumptions, for example, that you can put the gas as uniform in all the galaxies. So one has to make some further assumptions, and these further assumptions are sometimes valid and sometimes are no longer valid. It depends on the physics of cosmic rays. Now I'm trying to make you approach it to the simplest way. So in these simplifying assumptions in which the gas does not depend on R and Z, and you put a number, you say that hydrogen is almost 1 per centimeter cube and so on, one can use the orthonormal basis of the Bessel functions, which are the functions that are the basis in cylindrical symmetry. So, in this case, one can, first of all, for these simplifying assumptions, I told you, imagine that there is a symmetry on the phi angle. So, in one of the dimensions. And that the two coordinates that we are working on are R, which is the radius on the disk, and Z, which is the vertical coordinate. And the vertical coordinate is the one which maybe it's better to write than explain. So we have the possibility to write n as a function of R and Z as a development of a function which is a function of Z developed on the basis of Bessel functions. And I have set rho equal to R divided by the maximum disk of the galaxy, which is this more or less 20 kiloparsecs. And these J0 are the Bessel function of order 0, and Xi are the zeroth of the Bessel functions. So you can solve it analytically in this hypothesis and find an expression for an I of Z. And maybe it's not worth that I write all the details. You can find in the note. This is true, as I said, if the sources are Q disk R and they are set to 0 out of the disk. This is true for supernova remnants, pulsar, and spallations in the galaxy. I can maybe write the full solution. You can derive by yourself. I want to write the full solution because it gives us some hints to the physics that takes place. Having analytical solution is from one side a minus because you can lose some detailed description. On the other side, if you want to understand which are the main processes in this propagation history, it is easier to see than just a full numerical solution in which it is difficult to say, okay, at this energy, this is important and the other one is not, the other one process is not. So let me write the solution to the distribution of cosmic rays as a function of Rz in cylindrical symmetry. And the solution is this way. We have an exponential Vc over 2k And then we have the development over the Bessel functions of these two terms I will define in a while. We have QE divided by something that I call A, and we have the hyperbolic sinus of a factor which is SI L minus Z divided by 2, normalized to the hyperbolic sinus of SEL divided by 2. And this is, of course, multiplied by J0 xi rho. Now, this QE is linked to the term source, so I don't specify it, but it is usually it is a normalization times an energy dependence. And this factor that you see here, AI, is given by the diffusion coefficient, now I put the energy dependence, by a term which is this very recurrent SI, hyperbolic cotangent SEL divided by 2. And then there is another contribution, which is convection and the presence of inelastic destruction. And this SE comes out to be 4 times the 0th of the Bessel function squared divided by R squared plus convection squared, diffusion coefficient squared, and then there is a term which usually is negligible if the nucleus is radioactive. This K is our diffusion coefficient. I can maybe elaborate just a little bit on these sources. So the Q con E depends on the fact that the cosmic ray is primary or is secondary. If it is primary, it is a Q0, QE, and this is QE in the disk, which is a kind, it is linked to the development on Bessel basis. So my main aim is not to give you the very detail, but I want to try to understand some physics from this solution. And if it is instead a secondary one, now I just change a bit the letters, otherwise there is a confusion, but anyway, it is all the nuclei that give you this specific nucleus by spallation. So QE disk is the Bessel expansion for QR, and J is the nucleus. So you maybe remember, I can probably also go back to this situation that we have seen together. The situation here, this figure tells us that, for example, for protons, diffusion dominates, okay, which is this time which is very short. For iron, it is true, but only for higher energies. So let's try to put in an approximate situation in which diffusion dominates. So energy losses and even convection are not very relevant. So many of these terms can be put to zero. For example, this SI here, if convection, make this hypothesis that it is not very relevant over diffusion. This goes to zero, the nucleus is stable, and this is zero. And this number, SI, is kind of geometric term, which is given by the zeroth of the Bessel function, and R is 20 kiloparsecs. So it doesn't bring any special information on the physical processes. So in this case, SI is a fixed number. And so this is a number. And also this term is a number that only depends, let's say, on geometry. This number can change a bit if L is small or if L is high. But in a very approximate case, in which diffusion dominates, and in which the nucleus is a primary one, a proton, a helium, a carbon, then this quantity goes more or less as, let's say, maybe it's better to write that it is proportional to a sum over QE divided AI Bessel function. And this is proportional to Q of energy and inversely proportional to the diffusion coefficient. This was what I wanted to arrive at. So given this solution, this quantity here is not energy dependent, and it is mostly linked to geometry. But you have this Q, which is the source, and this A, which is, if this is negligible, A is mostly the diffusion coefficient. This is, of course, unless factors, of course. But this gives us the trend of primary nuclei as a function of the energy. This is a very important physical insight. If the source is a supernova remnant, and the acceleration is the first order Fermi acceleration, this quantity here goes as an energy minus gamma. Gamma, we don't know exactly. I told you that it is probably close to 2. And the diffusion coefficient is a function of energy. It is the rigidity, but let's put at high energy, it is the rigidity to delta, we defined it. And so it is E to delta. So we expect that in a first approximation, primary nuclei follow a power law, which is E minus gamma minus delta. So measuring a proton at high energies is, first of all, informative on its energy at source, the injection spectrum at source, and the diffusion in the galaxy. But if you measure a proton, or even a helium, you measure gamma plus delta, and it is difficult to disentangle the two. You measure, for example, a power of 2.6, 2.7, which is gamma plus delta, and it is not trivial. It is difficult to disentangle diffusion and acceleration from primary nuclei alone. Instead, let's keep this approximate reasoning. If instead we try to study a secondary nucleus, neglecting all the small or any other effects in the galaxy, this is, of course, Q divided by kappa, the diffusion coefficient, but this time Q is a secondary source. And the secondary source, written in a, let's say, a bit quick way, is proportional to a cross-section, which produces this nucleus, the density of the interstellar medium, but the energy dependence is mostly, there is some little dependence on the cross-section, but at high energy it can be neglected. It is dependent on the energy of the parent nucleus. So if it is a carbon that produces a lithium, the secondary source for lithium is this nuclear physics, but then there is the spectrum of the parent nucleus. And again, at a good approximation, the parent is a primary, is a carbon, is an oxygen. And this guy so let's write. This is the diffusion effect on the secondary nucleus when it is produced and starts going around in the galaxy. But its source is this one. And this one is this one. So, more or less, it is E minus gamma minus delta, E divided plus delta. Let me still write this way. So again, if you study a primary nucleus alone, it is very difficult to disentangle diffusion properties from the rest of the processes that are affecting it. But a way to disentangle diffusion is to use the ratio of secondary to primary. And the ratio of secondary to primary, now it is very easy, it is this one. Because the primary, more or less, of course, cancel out. So this is a bit a rough way, but it can be in some context not a bad way to understand real physics. And what physicists since a long time have used to understand diffusion or to try to have hints on diffusion is a specific ratio, which is the ratio of boron nucleus to carbon, the so-called B/C. So usually experiments measure the two independently, or more or less independently, and then publish data on B/C. B/C has often been considered kind of standard candle for cosmic rays, so the quantity to which people who have these big codes calibrate their free parameters. It is not sufficient only to have B/C, but the property of diffusions can be disentangled with B/C. And this is, you can maybe look at the right-hand side, many groups, including also the work I did in the past with some collaborators, Dario once, and other groups in the world, are predicting B/C. It's not the specific contributors, but what I want to show you is, first of all, this at your right is the B/C measured by AMS just very recently, very few years ago. So what you can see is that this ratio for a pretty huge energy range is measured at a very, very good precision. So also cosmic ray physics now is a precision physics. We have data till at least 1,000 gigavolt in rigidity, and this is a previous AMS situation. So really in the last years we have had a big improvement in the analysis, in the data. And at first order we can understand B/C using Fermi acceleration and isotropic diffusion. Anyway, many data are arriving from space, which do not only include B/C, but a lot of absolute fluxes for primaries, for secondaries, for antiprotons. And taken all together, it is almost clear now that we have to refine a bit our models to interpret them. But this will be left probably to your research activity in your next years if you are dealing with it. But my aim was for you to have clear what are the main processes, what do we expect, and what do we use to predict B/C. So arriving at B/C requires knowing many interactions, many cross-section. Boron is produced by some heavier patterns that we have to shape. So it takes some times in a PhD. There are colleagues of mine who spent all the PhD doing models for cosmic ray physics, because really it is very, very complex. But then you arrive at the prediction, and then you have data, and this is a lot of fun. I just take one more minute, and then we close this lecture and we close the school. Among the secondaries, we don't only have the nuclei that I listed before. We have antimatter. We discussed this in the previous sections, in the previous lectures. We have antiprotons, we have positrons, maybe antideuterons, even if we don't have data. And these are the secondary nuclei or antinuclei channels in which we also search from some dark matter modeling. And what you see here is some data, maybe better to concentrate on this, which are the data on the antiproton flux. And you see that also for this antimatter channel is pretty interesting to see that data are precise. So there is also for you who are starting your activity in research, a lot of perspectives and surely a lot of fun. I just wish to you to have so much pleasure in doing physics as I have done so far in my activity, which is really a very nice and beautiful part of my life. So the same I wish to you. Thank you for your attention, and a presto. In 2 minutes, because then I have to take the train with Francesca and our young boy, Francesca's boy, but I feel like an aunt in this occasion. You can write me, of course, emails if you want.